Hello, and welcome to the first of my videos of my maternity leave. Here we go, Chapter 6, Section 1. It's titled Random Variables. So first off, we're still in the probability section of our class. So with random variables, we're basically looking at numerical values that describe the outcomes of a chance process. What that means is, if you're doing a chance process, like flipping a coin, rolling a die, picking people to be in your sample, anything like that, that counts as a chance process. But the outcomes have to be numerical in order for it to count as a random variable. So like flipping a coin, because your outcomes are either heads or tails, does not count as a random variable. But like rolling a die, where you could land on the numbers 1, 2, 3, 4, 5, or 6, that counts as a random variable because the outcomes are numbers. So there's two types of random variables: the continuous random variable or a discrete random variable, and here are the differences. A continuous random variable can take on any number on a number line. So so the numbers 1, 5, 5.5, 5.675, fractions, decimals are allowed. It doesn't necessarily have to take place, but they are allowed. Versus a discrete random variable, you can only have whole numbers as your outcomes. So like rolling a die counts as a discrete random variable because you can only land on numbers that are whole numbers, like 1, 2, 3, 4, 5, or 6. So let's do a few examples here. Let's describe these as discrete or continuous. If our variable x stood for the foot length of a randomly selected student, so when we measure feet, I guess the length of your foot in inches and centimeters, whatever it is, we want to ask ourselves, like, can there be fractions or decimals? Doesn't necessarily have to mean that in our data set or in our outcomes that we will have fractions or decimals, but is it allowed? So when you measure how many inches your foot is, we can say like 7.5 inches or whatever. So because fractions, decimals work, then this would be continuous. Our next example, if x stood for the number of gas pumps out of 12 in use at a gas station at a time. So it's not like you can have like 5.5 gas pumps being used at a certain time. So in that case, whole numbers only, so this would be discrete. In our last example, we have x standing for the air pressure in a randomly selected tire. Air pressure, I believe, is measured in PSI. I don't remember what it stands for, but I'm pretty sure you can have decimals with it. Decimals, fractions, something like that, so that would be continuous. So the next thing we want to talk about and use with our random variables is something called a probability distribution. We've seen something like this before. It's very similar to a probability model that we had in Chapter 5. So a probability distribution is just a table that describes the outcomes and their probabilities. So our first row is just all our outcomes. In this case, they're all numerical. The thing with probability models, which was what we did before, was that it didn't have to be numerical. So that was the only difference between the two. But then underneath the second row, that's where we list out the probabilities for each of the outcomes. So back in Chapter 5, we also did a similar example to this one. We were using the example of flipping a coin 3 times and seeing how many times we landed on heads. So in this example, we're going to use x as our random variable. And remember, x has to be numerical, so we're going to let x stand for the number of heads you get when you flip a coin 3 times. So if we were to make a probability distribution for x, the number of heads that you can land on could be 0, 1, 2, or 3. Because like 0 is the smallest number of heads you can get. 3 would be the maximum since we're only flipping the coin 3 times. So in this first row for x, in my probability distribution, I have my different numerical outcomes that I could have for the number of heads that you land on when you flip a coin 3 times. 0, 1, 2, and 3. Underneath, we're going to put their probabilities. So to get 0 heads, that means you would have to land on tails, tails, tails. And there's only one way to do that out of the 8 total ways that you can flip a coin 3 times and land on whatever combination of heads or tails. So I filled out the rest of the probabilities as well. To get exactly 1 heads when you flip a coin 3 times, that would be like if you got tails, tails, heads, tails, heads, tails, or heads, tails, tails. And those are the 3 different ways you can do it out of the 8 total. Same thing with getting 2 heads at a time. It's like heads, heads, tails, tails, heads, heads, or heads, tails, heads. So 3 ways out of 8. And then the last one is if we were to get all 3 heads, so heads, heads, heads. There's only one way to do that out of the 8. So that's our probability distribution. The same rules apply as a probability model. So there's the 2 rules where all the probabilities that you have in a probability distribution have to add up to 1. So if we look at our probability distribution here, the 1/8 plus 3/8 plus 3/8 plus 1/8, that adds up to 8 out of 8, so that equals 1. Secondly, all probabilities have to be between 0 and 1, so you can't have any negatives, you can't have like 1.25 or something for a probability. And so all of our fractions are numbers that are smaller than 1, greater than 0, so that also meets the requirements. So using our probability distribution to then find some probabilities. First example, what is the probability that we get less than 3 heads when we flip a coin 3 times? So here we want to pay attention. When it says less than 3, we're not counting the 3. It has to be numbers that are smaller than 3. So here we're saying, like, for out of our x variables, we want to be looking at numbers that are less than 3. So that would be the 2, the 1, and the 0. So to find that probability, we would just take all the probabilities that are less than 3 and add them up. So 1/8 plus 3/8 plus 3/8 would give us 7/8. Second example, what is the probability that we get at most 2 heads when we flip a coin 3 times? So at most means that we can get up to that number, but nothing more. So at most 2 means everything up until 2. So 0, 1, and 2, again, if we add those together, we get 7/8. And then lastly, what is the probability that we get at least 1 head when we flip a coin 3 times? So at least 1 means you want 1 or more. So these are all words that you want to get used to. So at least, at most, less than, greater than, those are all words that you need to be able to think about. If we would get at least 1 head, then that means we want 1 or more. So we're adding up our probabilities with the 3/8, 3/8, and the 1/8. Still comes out to 7/8. Alright, so those probabilities were easy so far. Let's move on to slightly more complicated probabilities. These ones are just probabilities that you've done before, so a little bit of review here. But when we are dealing with specifically continuous random variables, so continuous random variables, remember we said those were variables where the x's could be fractions, decimals, things like that. So in that case, you can't actually make a probability distribution for it because our table would then be like way too big, because you not only would you have to have like 0, 1, 2, and 3, you would have to have all the decimals in between, which doesn't make sense. So you can't make a probability distribution for continuous random variables, only for discrete random variables. So in order to calculate probabilities using continuous random variables, then we have to look at areas under density curves or normal curves. So we're kind of back on that topic of normal curves. Remember, like the bell-shaped curve thing. Density curves, where we usually dealt with them in like rectangles. So here's my example. Let x be a variable that stands for the randomly generated number between 0 and 10. So if you're randomly generating a number between 0 and 10, first of all, you could have any number that's a decimal, a fraction that's in between 0 and 10. Also, because it's randomly generated, the probabilities of getting each number would be exactly the same. So in that case, it would be a uniform distribution. Remember, uniform means that all the heights, if you were to make a graph, all the heights would be exactly the same. So it would look something like this. So here's our graph. So 0 starts here, and it goes up until 10 because those are the numbers that we can generate randomly. And then we're saying basically any number in between 0 and 10, so from like, you know, even if you were at like 3.5, 3.556 or whatever, you still have the same probability of being randomly generated as, say, the number 7 or something like that. And so it makes this uniform distribution where the heights are all the way the same across. And so in a density curve, one of the rules was that the area of this curve, of this rectangle, should equal 1. Kind of like how all probabilities have to add up to 1 in a probability distribution. So if the area underneath this is 1, when we find the area of a rectangle, we usually do length times width, whichever, width times length, whatever you want to call it. So if the length here is from 0 to 10, that would make this a length of 10. What would the height have to be in order for it to multiply to 10? Or sorry, for it to multiply to 1. So we can think about it like 10 times what equals 1. So that should give you 1/10 or 0.1. So that's how we would figure out the height of the rectangle. And then from there, we are trying to find the probability of x, our random variable x, being between 3 and 7. So equal or greater than 3, but less than or equal to 7. So visually, that would look like this. So we're looking for this area between the number 3 and the number 7. And the shaded area that I want still makes a rectangle, so I just need to figure out the length times the height here. So the length here between 3 and 7, if I need to figure out the distance between the two numbers, I can just subtract. So 7 minus 3 would give me a distance of 4 times the height of 0.1. So when I multiply this out, I get 0.4. So that means our probability that x is between 3 and 7 is 0.4, or 40% if you want to think about this as a percentage. All right, for our last example, this time we are using a normal distribution to model our continuous random variable. So in this case, we are talking about the heights of young women. They can be modeled by a normal distribution, so that's the normal curve, the bell-shaped curve. They're telling us the mean is 64 inches and the standard deviation is 2.7 inches. We're trying to find the probability of choosing a young woman at random, and we're trying to find the probability that her height is going to be between 60 and 66 inches. So I'm going to start off with a drawing. Here's my normal curve. Just like what we used to do, we're always going to label our center of our normal curve with the mean, which was 64, and our standard deviation, which they told us was 2.7. So from here, we're trying to figure out the probability that our variable is between 60 and 66. So if we figure out where 60 and 66 are on our graph, then we can shade everything in between. So here we go, I've drawn in the rest of it. So 60 has to be less than 64, so it's going to be on the left side. 66 is greater than 64, so it's going to be on the right side. And then we're shading in between because that's the probability that we're trying to find. So this is the part where we have to think back to our normal curve chapter. So this is the part where we wanted to find the z-scores for each of our numbers that we're trying to find. So 60 and 66. We're going to find each of the z-scores, and then we have a whole table to use in order to find the probabilities. So just a reminder, the z-score formula looks like this. We have the value minus the mean divided by the standard deviation. So in this case, we can do it with the first number of 60. So 60 is our value minus the mean of 64 divided by the standard deviation of 2.7 gives me negative 1.48. So remember, with our z-scores, we wanted 2 decimal places for rounding. Okay, so that's my first z-score for the number for 60. We're going to do the same thing for 66. So when I did it for 66, I got a z-score of 0.74. Alright, so it's been a while since we've used these tables, but let's start with our z-score of negative 1.48. So if you remember, your table has a negative side and a positive side, so depending on whether you need to flip it over or not. Since our z-score was negative, we're going to look at the negative side. So negative 1.4, you're going to look at the first column to find your first decimal place, so negative 1.4. The second decimal place was an 8, so we're going to crisscross it with the 0.08 at the top here, and that should give us 0.0694. So there's that. Our other z-score was 0.74, so positive, which means we need to be on the positive side. And so our first decimal place is 0.7, and then our second decimal place was 4, so that would take us right here, 0.7704. Once we had those numbers, then since this was an in-between problem, we take our two percentages and we subtract the bigger one minus the smaller one. When I do those calculations, I get 0.7010. So that would end up being my probability. So you can also think about this as like 70.1%. So just a quick review of other normal curve problems that you might encounter. If we weren't finding an area that was in between, let's say we were trying to find an area that was only shaded to the left side. This would be the easiest one because you would find the z-score like you normally would, but there would only be one that you would have to find because there's only one number. And then when you look down at your table, whatever the percentage that you got was, that would be your final answer for when it's shaded to the left. If things are shaded to the right, this would be you find the z-score, figure out the percentage from the table, but then at the end you have to do 1 minus whatever percentage you got. So pay attention to how they want you to shade in the problem and then follow those steps. And that's it for 6.1. I'll see you next time for 6.2.